This program is brought to you by Stanford University. Please visit us at stanford.edu.
Just a couple of announcements. I will circulate with the sign-up sheet for students during 301 posters for next week's seminar, which in fact will be about solar. So if you would like to, please feel free to help yourself to one of these and take it back with you to the Wall Park campus and post it. Okay, so today's presentation is by Dr. Christina Archer, who is currently working at the Carnegie Institute, although she previously was in the Department of Civil and Environmental Engineering, where she did her PhD in Bathymetry. So we'll talk today about wind.
So I do have a microphone, but I'm not sure if it's working, so I'll try to raise my voice as much as possible. So thank you, everybody, for coming today. We'll be talking about wind power, and the first thing I really want to show you is a motivation. Why are we interested in wind power? And so let's see if this will work.
I think it was always misunderstood. People just do not seem to like me. I think I annoyed them. I got on their nerves. I don't know why. That's just the way it was. Yeah. Maybe it was too intense. Maybe I was too strong. I don't know. I really can't say. Yeah, it was lonely. Really lonely. But you get used to it after a while. And then, one day, everything changed. Somebody finally accepted me for what I am. Since I've got this job, life is completely different. I finally feel useful, good at something.
Oh, sorry. I couldn't help myself. This is basically the funniest video I've ever found about wind power, and so I thought I would use it to introduce my talk. I'll be talking about four topics. First, of course, an introduction to wind power, and then I will focus in on the single most important problem with wind power, which is intermittency. And related to that, I'll mention some storage issues and some interconnection of farms option. I'll talk also about some new wind power technologies that you may have never heard of and might sound somewhat futuristic, but you never know. And finally, I'll try to put everything together in an integrated view of how wind power can play a role in a future energy system. So let's start with the first part, introduction to wind power. I wanted to show you these pictures to give you a sense of what kind of turbines I'm talking about. These are very, very large machines. This is the blade of one of them. It's about 32 meters wide, and this is a human being standing by it, just to give you a sense of how big they are. The hub is at about 80 meters above the ground, so that's something like a 20-story building. So this is a massive structure. And offshore applications are becoming more and more common nowadays, and this is what it will look like with turbines in the water, basically. Wind power has been phenomenally increasing in the last years. It started in the late 80s in the US with very little development except for California, which which had a lot of incentives from the state. So you can see how for about 15 years, all the US production was basically in California. But after that, Texas actually took off and is currently the largest, the state with the largest capacity for wind power. And all the other states have grown up as well. And last year, the 2007, was probably the gold rush year for wind power, with a growth of something like 45% with respect to 2006 in the US only. Why is there such a phenomenal growth? And the reason is that the wind resource is really huge, and I'm going to try to put that in perspective with this slide. If that square is the global electricity demand, which means the electricity that the entire world needs on a regular basis on average, and this is the global energy demand for all uses, including transportation, including heating, if you were able to put the wind potential there, that's what you would get. It's 72 terawatts. And to give you a sense for what that means, a terawatt is 1,000 gigawatts. And modern coal-fired plants are about 1 gigawatt. So 72 terawatts is the equivalent of something like 72,000 coal plants. So it's a huge amount of power available, theoretically. And by comparison, this is what is currently installed worldwide. It's less than 2% of the electricity demand. So. Another good news is that the cost of wind power is decreasing. It has been decreasing in the US since 1999 from something like 6 cents a kilowatt hour to less than 4 in 2006. So that's good news as well. When I say cost of wind power, I mean the cost of producing a kilowatt hour. That's not the cost you pay on your energy bill. And then finally, not only there's a lot of wind power out there, but it's also located, it's very ubiquitous, so you can find it easily in a lot of places. So we produced maps such as this one for the entire globe, actually. And the idea is that for each dot, there's a location that has measurements of wind speed. And we interpolated that wind speed to the 80-meter height, which again is the height of the modern turbines. And we came up with some sort of an annual mean 80-meter wind speed map that tells you which are the best locations. So for example, for the US, as the color gets darker, the locations get better. And what really stands out is the center of the US, basically, which is sometimes called the Saudi Arabia of wind power in the US. But other important information that came up was, for example, that both coasts, the northwestern and the northeastern coasts, are very good sources of wind power potentially, especially offshore. So you can see how most of the coastlines are actually very dark green. That means that they're very good for wind power production. And a particularly interesting finding was that there's actually potential in the Gulf of Mexico, which was something that people didn't know before. So we decided to investigate a little better what the offshore potential is. And with colleagues at the University of Delaware, I looked at the East Coast potential for offshore. And what we did is, the first constraints for offshore is the bathymetry. You can't build your turbines where the water is too deep. But fortunately, the East Coast is actually ideal. And the color on the map here shows you depth up to about 100 meters. So there's a lot of coastline that is deep, that is not too deep and allows for offshore development. We looked at about 26 years of data from buoys. So this is a observational-based study. And we looked also at exclusion areas, including, shipping lanes, areas that were devoted to tourism for beaches, bird paths, areas that, for whatever reason, the military didn't want to allow for public usage. And the values were something between 46 and 10%. And these are the three depths we looked at. 20 traditional technologies, 20 to 50 is a light structure for wind, an extension to 50 to 100 meter, which was a prototype at that time. And this is the number we came up with, 330 gigawatt of potential, which is more than enough to cover all the current demands for that area, which is about 185 gigawatts to about 212. So as you can imagine, the potential is huge, and we didn't expect to find that. we looked then at the California potential, this time with a new approach, which is based on MM5 simulations. And we looked at about 2 years of data in the summer. The problem with California is that the bathymetry is not as favorable as the East Coast. So basically the bottom of the ocean goes down really steeply. So there isn't that much coastline that's good. And we looked at depths up to 200 meters, and we looked at this floating platform technology, which is somewhat a prototype at the moment. But the idea is to have a platform that floats over water with a turbine mounted on top. And these are the numbers we came up with, 23 to 33 gigawatts, which is about a tenth of what the East Coast potential is. So it's not as large as the East Coast, but nonetheless is more than enough. It is about enough to cover the current electricity demand for California, which is about 34 gigawatts. Okay, so that's all I wanted to say as an introduction and give you a sense of what kind of studies we've done. Now we'd like to talk a little bit about wind intermittency. And what do I mean by that? Wind is intermittent, and that's because it's its nature. It's annoying, as the movie showed. You know, it comes and goes. And this is a typical. I picked a week of data from Dodge City, and you can have big spikes. You know, wind speed can go up and then come down, and that's not something you want to have your electricity supply to look like. But if you thought this was bad, wind power is actually even worse, because wind power is proportional to the third power of the speed. So any little variation in speed gets amplified because of that. So you can see how, for example, on this day, you can go from 0 power to maximum power, in this case, 1.5 megawatts, in like a few hours. And that's something that you absolutely do not want to have as a utility manager. So how can we mitigate this? And the first solution that comes to mind is storage, right? If we were able to store the excess energy or the excess electricity that we have at times and use it later, that would smooth out everything. And of course, having a battery would be a perfect solution, except it's still kind of expensive, especially for large-scale applications. Other solutions that are common, I mean, I don't want to go in detail into this, just give you a brief sense of what's available. Pumped hydro is one of them, and is based on the idea that there are 2 reservoirs of water at 2 different levels, one here and one there. And what you do is you use your excess electricity that you may get at night, for example, from wind. You use that electricity to pump the water to the upper reservoir, and you use that in the afternoon when the demand is high and the cost is high, and you smooth out your supply that way. Another method is compressed air energy storage, which is becoming more and more popular, I would say, lately. And the idea is that you can use the excess electricity that you may have at night to pump air underground in an existing cavern of some sort. And then that air gets pumped out in the afternoon when you want to smooth your demand. It goes through a generator and a turbine. It still needs natural gas to heat up the air. But you get overall a very good efficiency of something like 80%. So as promising as this is, there's only something like a couple of currently existing installations of this system, whereas the pumped hydro is much more common. There's about 100 worldwide. But I want to also mention something that's more like at a prototype stage at this moment, but it was mentioned by Google when they gave their talk about a month ago here. So there's this idea of the vehicle-to-grid. And it sounds kind of funny, but if you think about your car has a battery, and your car is parked for something like 23 hours a day. And it's probably parked in a place that is not random. You know what it is most of the time. So if there was a system in which you were able to exchange information with the system about where your car is and how much you're willing to discharge your battery for the good of the system and be paid for that, you can imagine how the over 100 million vehicles in the US can actually supply a huge amount of storage. And this is an application that is at the moment just thought for some kind of a emergency solution. So to be used only on the hottest days when there's a high possibility of a blackout if nothing else were implemented. But again, you can imagine how if there are more plug-in vehicles and eventually more electric vehicles, the size of the battery grows, and you can actually provide an interesting amount of storage that way. So you can look at V2G online at the University of Delaware for more details about this. And alternatively, you can also think of hydrogen. So if you could generate hydrogen cleanly from electricity from wind power via electrolysis, and now all of a sudden you have a fuel that you can use when you want to produce the additional electricity that you don't have. And so you can do that on site on a wind farm. And that's something that they're studying right now at the National Renewable Energy Lab in Colorado. They're looking exactly at that. Or you can also use hydrogen as a fuel for cars. And this is myself driving a $1 million hydrogen vehicle a year ago, which hopefully will come down in price. Otherwise, there won't be any application for that. But you can see how hydrogen can actually be can be an interesting contributor to this problem of smoothing the output. But now I've talked about other people's ideas, and now I want to mention what we have worked on, myself and Mark Jacobson here at Stanford. We have looked at this idea of connecting farms together, and this is kind of like what it is like. So if this is what the grid currently looks like, and these little houses are like urban centers, and the lines are some kind of a boundary, say a state boundary or a utility jurisdiction boundary of some sort. The way the system works right now is that there's typically a big transmission line, a high voltage line, very big and very intrusive in the environment. And there's smaller distribution lines that allow the electricity to flow to the urban centers that need it. And if there's any wind power in the area, because of the cost of transmission, the way it works typically right now is that the wind farm feeds directly the nearest urban center, and that's all, because it costs so much to build this that they don't want to go any farther than the minimum distance that would be useful. And you can imagine how if, for example, this city had already bought all their electricity from whatever sources, and at 3 in the afternoon, all of a sudden, this farm has a lot of power that wants to give the city, but the city has already paid for all its electricity, and they're going to have to, the wind farm basically has to spill its power. And so all that electricity is to go to waste. You can imagine how if instead we were able to connect the farms directly to the transmission line rather than to the nearest urban center, then all of a sudden there's no such a case as the one that I just described. All the electricity produced by the farms is available for everybody at all times. And you can imagine that there are several benefits that you can get from that. And we studied, as an example, a large area in the Midwest, Texas, Oklahoma, Kansas, Colorado, and New Mexico. And we picked sites such as these indicated with the plus sign that had a good wind speed to start with. So you have to site your wind farms in locations that are windy enough to be economical. And the threshold is something like 7.9 meters per second on average at 80 meters. So we had 19 of them, and the idea was, let's start from one. So that was Dodge City. And then let's imagine that we connect now 3 of them. Now we have an array of 3. And then we have an array of 7, and then 11, and so on, up to 19. And let's see what happens to the energy output once we enlarge the area. We actually looked at not only this geographically larger area that I showed here, but I actually looked at all the possible combinations of all of these sites together, which is something like 75,700 combinations. But I'm going to show you just one of them for today. So a smart way of looking at the results, I really like this plot. And the idea is that I get the power output as a function of time for an entire year. In this case, was the year 2000. So I have all the hours in a year, and I measure them by percent. So, 70% of the time, 80% of the time, and so on. And I rearrange my power output in such a way that I first plot the higher power days and the other days in decreasing order. So I get a curve like this. That shows me a lot of information. The first one is that if you have only one site, about 15% of the time you produce no power. So 15% of the time you cannot provide any electricity. That's a huge amount of time, as you can imagine. And conversely, on about 15% of the time, you get maximum power from your site. But this is what it looks like. What happens if you connect now 7 sites together? What happens to the curve? Okay, this is what happens. Basically, you're moving energy from the windy days to the less windy days, and you're starting to reduce the number of hours with no power. And when you have all 19 of them, you actually have no time with no power. And so that's the benefit. And of course, to get that, you actually have basically no times with maximum power. But the idea is that this curve is smoother, and you basically reduce the extremes of your distribution. An interesting advantage is that now you can look at how reliable is the output from this system. So I'm showing you here this 87.5% magic number. 87.5% is because a typical coal plant in the US is down for either routine or unplanned or scheduled maintenance for something like 12.5% of the time. So that's 100 minus 12.5 gives me 87.5%. So that's basically the comparison that I'm doing in terms of reliability. So a typical coal-fired plant is reliable 87.5% of the time. So for that percent of the time, if you only have one site, the power that you can promise and be reliable is 0. There's no way on 87.5% of the time you can produce anything. And that's what the way wind power has been thought of typically. There's no way it can provide reliable power because of that. But as soon as you put 7 sites together, now this is non-zero. And when you have 19 of them, you can actually provide something like, 200 kilowatts out of a maximum capacity of 1,500. And if you consider that on average this system produces something like 600 kilowatts, you can see how a third of the average output is actually reliable. That means that it can actually be used as base load. As long as the terms are clear, I'm not talking about a base load of the entire capacity. I'm talking about a small base load, but nonetheless reliable. Finally, there's also another benefit that this diagram allows me to show you. And that has to do with transmission. Now, suppose that for whatever reason, your transmission line cannot transmit 1,500 kilowatts of power, can only transmit 1,200 here. So if you only have one site, all of a sudden, about 10% of your energy has to be spilled because it basically cannot be transferred to wherever you want it to go. But if you have 19 sites, now the transmission line would only lose, with that small transmission line, you would only lose 1.6% of the energy. That means that you can actually plan a smaller transmission line of only 1,200 and losing only about 2% of the energy as opposed to losing 10% of it. So that there's an additional benefit in interconnecting the farms. Basically, you can connect 5 for the cost of 4 or something like that. Okay. So what about the smoothing effect that I mentioned before? So this is the diagram that I showed you earlier with the big spikes. Let's see what happens now when we actually have an interconnected system. The green line shows 8 sites, and the 19 sites is in black. And it's very, very much improved. So these big spikes that we had before are basically gone. Same here. If you were expecting a flat line, you're not going to get it. This system improves reliability and improves the interconnection, the intermittency problem, but it doesn't take it away completely. Just to show you that I'm not talking about fried air or anything like that, this is a real case in Spain. That's exactly what happens. All the wind farms are actually interconnected by a single utility system, and this is their output, which is very flat on a given day. Okay. Now the more fun part of this talk. I want to mention some new wind power technologies. And this is what they look like. So I know, it looks like futuristic drawings of some sort. And there's basically a lot of interest in high-altitude wind power. And the idea is that wind speed goes up with height in general. So the higher I go, the more the wind, the more the energy I could get. So how high do I need to go? And how can I get that energy? So there's this technology called kite gen. And it's basically technology based on kites, as the word reminds you of. And the idea is that they have a system of kites. Each kite is mounted at the end of these arms. And depending on the wind direction, the carousel spins and generates electricity. And they're targeting heights of about 500 meters to 1,000 meters above the ground. Whereas this ambitious project, it's called Flying Electric Generators. They're aiming at the jet streams. The jet streams are these powerful currents that are found in the atmosphere. And if this works, it's great. It's basically 4 helicopters, in a sense, that take energy to get up to the elevation where you want them to be. But after that, they generate electricity. And they are they self-sustain. They don't need electricity to stay up. As you can imagine, there's a small problem with the tether that has to be something like 30 kilometers long and has to be able to deliver the electricity down. But once you solve these minor details, it's a great solution, isn't it? No, I just want to show you why this is actually interesting. And I'm just picking a point in New York City, and I'm showing you wind power density as a function of height. Wind power density is a more conservative way of showing you wind power because it takes into account that as you go high, the air density is smaller, and so the power you can get is smaller. And I'm showing you here different percentiles. So for example, this line, the blue line, means that at each given point, you get that density or more on 32% of the time, on 50% of the time, 68% of the time, and so on. So let's just look at the 50th percentile. So near the ground, you get something like less than half of a kilowatt per square meter. But if you go up to the jets at about 9 kilometers, now all of a sudden you get something like 8 kilowatts per square meter. And that's an order of magnitude or more of power. It's a huge, huge amount of, it's a huge, huge benefit. And that's at the 50th percentile. These 5% doesn't even fit in my plot. These are basically very strong winds, very intense cases that may or may not be good. They might be too strong to actually, they might even damage the system. But anyway, so if you focus on the 50th percentile, we already knew that that kind of makes sense to go high because of that multiplication by 10. But another interesting finding is that it's pretty constant between 500 and 2,000 meters. And that's something that is not only valid in New York, I found it at other locations as well, which means that, you know, if you want to go above 500 meters, it might not be a good idea unless you're really willing to go high to above 2,000. Of course, there are geographical differences. Not every location is as good as New York. I'm showing you here the 50th percentile of the entire planet at 10,000. And it looks an awful lot like what a jet stream would look like. So you have maxima to the east of the continents in the northern hemisphere. You have a maximum here over Africa, exactly where the jets are found most commonly. So you can see how Japan is an amazing place for high-altitude wind power. Now, you don't necessarily have to go all the way up to the jet streams to get that strong power, because sometimes you can have local conditions such that the wind is actually higher at lower elevations. So that's what we looked at in this plot with optimal winds. So the idea is, what if I actually have which is actually reasonable, what if I can actually reach the height where the winds are maximum at all times, rather than just staying at a fixed height? So you will get, you know, now all of a sudden the blues are gone, and you get higher areas that are very good for that purpose. Not only that, but you also need to be careful about this global warming of ours, because the jets are actually being affected by global warming, or that's what we are suspecting. So I'm showing you here some trends in the wind speed of the jets. So I've looked at about 25 years of data, and I've tried to determine, are the jets stable and steady at the same location, or are they moving? And as you can imagine, this can have a lot of implications for high altitude wind power as well as for our climate. So I'm showing you here these trends in which greens mean that the speed is actually increasing, and blues mean that the speed is actually decreasing. And you can see there's a lot of variety worldwide, but interestingly enough, look at what's happening here over Asia. There's big areas of green poleward of big areas of blue. And this same dipole, blue-green, you can also find here in the Atlantic and here in the southern hemisphere. So what that means is that if the speed is going up towards the pole and is going down towards the equator, that means that your jet is actually shifting towards the pole. And that's exactly what's happening. And that's what I'm showing you here. I'm showing you here a global average of these latitude anomaly. So I take the latitude of the jets, and I take the mean away, and I look at how that difference basically is a function of time. This is for the December, January, February. But it's the same conclusions are valid year-round. So NH is the northern hemisphere jet, and SH, by comparison, is southern hemisphere. And T is tropical, and P is polar. So I've looked at these three jets, and as you can see, in the northern hemisphere, the anomaly is positive. That means that the jet is going to the pole. And in the southern hemisphere, the anomaly is negative because it's shifting towards the south pole. And this is a scary finding, actually, because it's very consistent with other signals of global warming that are projecting the same type of signal. For example, the widening of the tropics is one of the well-known consequences of global warming. As the tropics widen, they push the jets away, and they push them towards the pole, and that's exactly what we're finding. Furthermore, the altitude of the jets is changing as well. And again, this has implications for high-altitude wind power. How high do we need to go? And what if this height actually changes? And the way to measure height is with this weird pressure metric. Basically, as pressure goes down, the altitude goes up. So that's why I'm showing you hectopascals here with decreasing values as you go up. And again, in December, January, February, which is the summer in the southern hemisphere, the jets are actually rising. And this is very strong signal in the southern hemisphere pole, maybe less strong in the other two jets. But also on an annual basis, this is the same signal that I'm finding. So the jets are rising. And again, this is not surprising because a rising of the tropopause is a signal of global warming that's well known. Okay. So we're almost at the end. We looked at all these technologies and how great wind power is. But now there's one more barrier that's actually very important. And the idea is that there's often a mismatch between the wind power production and the demand for electricity. And this was an important case in 2006, in July 2006, here in California. We had a very strong heat wave, the strongest heat wave in the last 50 years. And it caused all kinds of problems to the system, but actually it wasn't that bad as it was by comparison in 1999 and 2000 when we had blackouts. We didn't have as many blackouts for this. But I'm showing you here about 5 days in July during which there was this heat wave. And the blue line represents the load, basically how many megawatt hours the system was requesting for air conditioning mainly. And on the right-hand side, I'm showing you the Altamont capacity factor. Altamont is a very large farm that's in the between the Bay Area and Central Valley. I believe it's the largest farm in the world in terms of land occupation. It's really large. And if you take what's the freeway, 580, going to Sacramento or going to Livermore, you actually see all these beautiful mills everywhere, windmills. But anyway, a capacity factor means what percent of the maximum capacity was produced. And as you can see in these 2 days where the demand was super high, there was basically no wind. Wind was less than 15% of the capacity. And also in general, the trend is like the yellow lines, the yellow bands are the daytime. And you can see how there's very little wind in general during the day, and the spikes tend to be at night. So it looks like, at least for Altamont and other locations, there's this mismatch between the time when you want the electricity and the time when you can actually produce it via wind. But I put these yellow bands to kind of suggest that that's the time when the sun is up. And during a heat wave, chances are it's really, really sunny. And so the idea is, let's put together renewables, several of them, and see what happens. And that's kind of like the vision summary slide for you today. The idea is that we can do a lot with renewables. So we have wind, solar, hydro, we have tidal waves and geothermal. All of this produces electricity to a transmission grid. This is just a symbol for transmission. This can be, hopefully, is a new transmission system. The current transmission grid is really obsolete and doesn't work very well. But even if we just had that, once we add all them together with a smart metering system that allows electricity to go back and forth from a house, for example, so that with your solar panels, you can actually produce electricity that you don't need, and you take it back, and you get credit for it, and so forth. We have more plug-in hybrids or electric vehicles that can be used in a clean manner. And if that's not enough, which probably won't be enough, here's other little additions that I mentioned today. For example, the kite generation, which here means like large scale, but it can also be small scale. Why not? Fuel cells can have a contribution in this. They can be put in between the wind power and transmission to smooth out the output, as I mentioned earlier. We could need some storage to help us. And I just found this interesting application. There's a company that sells these kites, these sails, whatever you want to call them, that actually help giant ships in their paths. And they guarantee some savings of the order of 30% in fuel economy. So 30% in the total cost of the fuel for this ship is not that bad. And it's kind of going back to the origins, I guess, to the way ships used to go. Okay. Now, in conclusion, the wind resource is really, really large, and the number to take home is 72 terawatts. You need maps. You need to know where to put your farms. And 80 meters is the height of the turbines nowadays, so that's kind of like the target height. There's a huge resource in the US offshore, although there's not yet a single offshore farm in the US. Hopefully in Texas it will happen. Intermittency can be ameliorated by interconnecting farms, among other technology. And again, I want to put the emphasis on improved, not taken away. So not only no single renewable or no single storage system, but no single traditional energy system can actually be the solution for our energy problem. But the idea is that perhaps, and I'm saying perhaps, because I want to look at that next, maybe a mix of renewables can do that. And so invite me again next year, and we'll see if that works. That's it.
Talk about alternating renewables or mixing them together. In terms of like offshore and tidal would seem to go perfectly together. If you're putting the infrastructure in place, like interconnectors and so on. Have you looked at whether the areas for optimal tidal power coincide with optimal offshore wind power? Or they tend to not correlate or be mutually exclusive?
I wish I could answer. I have not looked at that, so I'm sorry.
Do you have a cost figure for the different types of wind? For example, I understand it's about $1,000 a kilowatt for a land turbine, but what about a shallow offshore turbine versus a deep offshore versus a floating turbine versus a...
Well, some of these technologies are really prototypes, so there's no cost. But I would say offshore, let's say a factor of 2 is safe. It's probably a too high estimate.
you have an estimate of 72 terawatts possible. And I'm wondering what assumptions are made when you do these calculations. I mean, one can envision a complete front wind and putting the windmills basically wing to wing. Okay. And then another patch 100 feet behind them, and so on and so forth. So somehow there must be some sort of a factor that you assume. I'm assuming. How does that work?
So that number was based on the following assumption. So I looked at 80-meter wind speed worldwide, and I determined that about 12% of the sites had enough wind speed to be economically feasible. So basically, you look at the annual average, and you take sites where it's greater than 7.9 meters per second. So that's about 13% of the land. Now, so that's what I imagined that I would cover. Let's cover 13% of the land with turbines at a density of 6 per square kilometer. And that 6 is a number that has some turbulence and reasonings behind. And the idea is that you want to have something like 4 diameters in this direction and 7 diameters in the direction where the wind comes from. So that turns out to be about 6 per square kilometer. So once you do that, then you can take a, an average turbine as a template, as a case, and you use the average speed that you get, and you take into consideration the statistical distribution of the winds, and you come up with that number, basically. So I'm not covering the entire planet, so I'm taking 13% of the land only. So the land is 25% of the planet, and I'm taking 13% of that, and I'm covering with about 6 turbines per square kilometer. Joe?
Just curious how that compares to the total frictional dissipation of the winds.
Yeah, that's a very interesting question, and a question that I always get asked. And people ask me, so are we going to slow down the winds near the Earth and so on? And some people have actually looked at that, and they have taken some they've covered the entire North America with farms, and they got a reduction in wind speed that was on average less than 5% near the boundary layer. So even with these gigantic farms covering entire North America, so the effects are really, really minimal. That's kind of the message to take home. When you put these arrays in the jets, since the jets are such important driving factors for the weather, then the situation might change, and that's what we're looking at right now with Ken Caldera, my current boss. So.
What's the optimal size for wind turbine?
The optimal?
So a picture of a 1.5 gigawatt turbine.
Megawatt.
How does it vary with size, of course?
Well, there's this kind of like back of the envelope number that was mentioned before of about $1 million per megawatt. So the biggest turbines I've heard of are about 5 megawatts, and they are about 100 meters tall and about 100 meters in diameter, let's say. At $1 million per megawatt, so it will be $5 million per turbine. Oh, the cost of production? It kind of depends. The average for the US that I showed you for 2006 was about 4 cents per kilowatt hour cost. And they looked at a variety of turbines, so I couldn't say which size. But these 5 megawatt turbines are still not really used that much, so the average size is 1.5 megawatt for relatively modern ones.
If it's 4 cents, why does wind power need a subsidy?
It doesn't need a subsidy, but every other form of energy does, including coal and oil and, So we have to be fair.
What are the issues with wind power that you see in developing countries, say like India and China, where even in those countries for the last 5 years, the growth in wind power has been phenomenal? And there are 2 specific issues that I'm really concerned about. One is the other environmental impacts of wind turbine, because they're huge structures, and there have been cases in India where they actually affected the groundwater patterns, and the people in villages were actually they didn't get water.
They affected the water.
The groundwater patterns.
The groundwater patterns?
Yes, because the structures are huge.
How can that be?
And the second issue that I see in developing countries is the capacity utilization factor. The energy generation, it's very, very low. I mean, the factor is like 15% at most. what do you see, what are your thoughts on these issues, and what do you see the potential of micro or small wind turbines ranging a few kilowatts in these situations?
You're asking me difficult questions here. In China and India, I've looked at some maps like the one I showed you, and I didn't find a lot of sites that were good. But nonetheless, there were several locations that were ideal. And China is developing a lot of wind farms, so it's definitely interested. India, I'm not sure, but I did give my data to some Indian companies that contacted me. So I am aware of an interest, at least, in developing wind farms. There's all kinds of problems. Renewables, they kind of need an efficient grid because the energy they produce is available right away. You have to put it on a grid right away, and if your grid is old, that could be a problem. So I don't think it's super easy for India and China, but there is definitely interest. And it's interesting that you're mentioning the smaller scale turbines. That's something I did not look at in detail, but it's definitely something that's developing. You can actually buy a wind turbine commercially right now online, and they will ship it to your home, and you can install it in your house. Of course, we're talking about much smaller structures, much smaller outputs, and I don't know how reliable they are, but they are of interest and they are developing. There's actually a project even in New York, for example. They want to build a stadium for whichever sport, I don't remember, but they're planning to actually put the turbines within the structure of the stadium, these smaller turbines, so that the energy generation would be part of the structure itself when it's built. So there's definitely interest, and I would say it makes sense, especially in remote locations. There are some Indian tribes in California that are trying to build some smaller turbines for the same idea. So I would say it's a good idea.
I was puzzled by what you said about interconnected wind farms. I looked at the data from Germany, from this Eon Netz, if I pronounce it right, facility, which is the biggest wind turbine outfit in Germany. They say they have a capacity factor on the average of 20%. So that seems to me somewhat inconsistent with what you said. I'll send you a slide from that.
Yeah, no.
But I don't understand the difference between Germany and what you said.
You are catching the right point. So there's a big difference between Germany and the sites that I showed you. The Midwest US is really a fantastic area for wind power. And it has a lot of good properties, among which this small correlation among sites. That's why I get very, very, very high capacity factors. I get something like 48% capacity factors. That Germany gets 20, I'm like, no way, that's such a disappointment. 20% is the number that was common in the 90s, I would say, but with modern turbines properly sited, I have a hard time believing that they would get 20%. So the number I usually use when I don't know anything else is 30%. And, but if you're really good and you place them right, you can get 40 to 48. So.
A related thing is, I understand Denmark has a goal of 50% wind power. They're at 20.
They're already at 20 now.
And they had a goal of 50. I mean, that's much higher than, for example, what your data would suggest is reasonable.
Yeah, Denmark is amazing, and there's a lot of offshore development, and it's really a windy place, so it makes sense. And I remember receiving an email last winter on a day that there was a storm or something was going on, and at that moment Denmark was 100% on wind power for that 1 hour on that day. So I'm not surprised that they're aiming at 50%, although it's ambitious. Bruce?
Do you have an estimate for the global offshore resources?
I do. I have it somewhere in there. Maybe we'll talk about it later.
Does anybody try to put together smaller systems, say on island nations and trade winds with a mixture of renewable storage and wind? It seems to me that right away you come out positive in terms of economics with that, because the price of fuel is so high in those areas that it would be a natural place, it would be a perfect test bed for these systems.
I'm not aware of that, but yeah. If you can find locations where the winds are persistent and steady, I would say I would sacrifice strength or you know, windiness for steadiness. So if I were to pick between two sites, one is very windy but is intermittent, and one is less windy but more steady, I would definitely choose steady. So trade winds would be perfect.
If you're looking for a specific location, where would you find that information? About the wind power and the steadiness?
Where you would go on the internet to find it?
Yeah, you showed wind maps before, yeah. Right? I mean, is there certain sites you go to?
Well, you can go to my website. And I have maps for all over the world. But probably an even better site is something I became aware of a few weeks ago. It's 3tier.com. So 3 like number 3 and TIER. It's a private company that has done some amazing work with mapping. And they've taken model outputs as well as observations and as well as Google Earth interface, and they're really good. So, and otherwise also NREL, the National Renewable Energy Lab, they were the first to really develop these detailed maps of winds. And they are a little, sometimes they're 50 meters as opposed to more like 100 meters like we're interested in now, but they might have done something new. So, sorry that I...
No, that's fine. From a utility perspective, how much intraday or intraday, I'm not sure which one it is, but within a 24-hour period, variability, are they willing to stand from a renewable source to say, hey, I'm willing to commit X% against this? Because you look at it, you can see a 50% variation within a couple hours or within minutes even. How much do you need to dampen that down to where they're like, okay, I'm comfortable, I'm going to give it 10% or 50%?
They're comfortable with 0% variability, obviously.
I'm joking.
I'm joking. It's a question that I probably don't know how to answer precisely, but there's definitely a lot of resistance by the utilities company in implementing more wind because the system was designed like say, 50 years ago or so, to rely on a fuel or a system that you can really dial up and down depending on your needs. And it's wonderful and it works beautifully. And so now with renewables, you have to have a system that is flexible instead. So not only can you not do that dial type of operation, but you also have to plan for it in advance with all the forecasting error issues related to that. So there's a lot of opposition in the utility groups because of that. But at the same time, I see it as a challenge and as something that can be done. We need to be flexible. You need to watch Incredibles, and that's what Elastigirl says too. You need to be more flexible. It's the only way to go.
Right now, how willing are they to support it? So I mean, like the Altawah Pass
right
example,
now, would they
it was like 5% of total demand you were showing, which is pretty.
Right now, I really would say that they consider the wind input as a it's the same as a negative load. So it's like a variation imposed on the demand.
Okay.
So they don't treat it. It's just like, oh, I thought the demand was going to be 100. It's now 99 because I have 1 megawatt of wind. So it's basically an annoyance on the load.
So like 5%.
There's a series of byproducts from this, such as people talk about killing birds, noise from these machines, and locality, all those things.
I think I might have a slide about birds. I love it when I have a slide for voice. So the issue of avian fatalities always comes up, and I think it needs to be put in perspective. Really, really, it's very important that you compare numbers and don't just focus on that against wind power. So in the US, there's something like, let's take the highest number, 40,000 deaths per year from wind turbines. And that compares with 50 million deaths a year by communication towers, like cell phone towers. I don't have numbers for number of birds that are killed by windows in our houses, but I would say a bird a year in my complex. So, and the average pet kills 2 birds a year. the average can't. So really, when you put, and now what about the bird flu? 200 million deaths. And we're talking about saving something like 50,000 to 100,000 human lives a year by implementing more wind power technology. So this is work done by Mark Jacobson. I'm just reporting it here. So the problem with California is that Altamont, which is the biggest farm, is on the path of migratory path of some protected species. And so when you kill a robin, it's no big deal, but when you kill a bald eagle, obviously it's a totally different issue. But it's so California, it's just at that farm, and it puts a shadow on the whole system. Nonetheless, they're doing a lot of measures in Altamont. They are shutting down something like 50% of the turbines during 6 months a year when the birds are more likely to fly by. And also, the higher the turbine becomes, the slower it turns, and the easier it should be to see by birds, although the speeds are still very high.
I think in the interest of time, we should maybe stop at that point. Well, thanks.
Okay.
Next week, solar.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.